Can you guys see that? So, I have a question for you. Can you guys see that okay? I can't write on the thing, so. There's 3 balls right here. We're going to release all of them at the same time. And the balls are going to travel down these 3 paths. Path 1, path 2, or path 3. Can you see that? So I'm labeling them 1, 2, 3. Which ball is going to win the race? Number 1. But this is, the shortest distance between two points is a straight line, right? So why wouldn't number 2 win? Because it has to travel the shortest distance. So who says number 1? Who says number 2? Who says number 3? 1, 2, 3. All right. Number 1. Okay. I got 2 answers. No one else is answering, right? Okay. So we're engineers. Let's not guess, right? We're engineers. Let's compute the solution. So the problem that we're faced with is a famous problem called the Bocristochrome problem. And it's basically the problem of if we have 2 points and a particle that's going to travel along those points under the action of gravity, what is the fastest path between the 2 points? Meaning the fastest path in terms of time. So the question is, a particle traveling from point A to B, what is the path that will get you there the fastest? Okay? And so if we call our path S, and we zoom in on a little increment of S, ds, we can approximate ds as the square root of dx squared plus dy squared. Right? And I'm going to write well, basically, if you divide by dx, you can show that this results in 1 plus y prime of x squared. Okay. And so the time, this is just an approximation to our path ds. And we can show that the time it takes is equal to basically, heuristically, the distance traveled over the velocity traveled. Okay? So then mathematically, along our path, that'd be from point y1 to y2, ds is the total path length over the velocity. That's equal to y1, y2, 1 plus y prime x squared over v. All right, and then just from statements of, we're just talking about a particle here. So we can say, just from conservation of energy of a particle, that basically says the kinetic energy is equal to the potential energy. Well, then that's 1/2 mv squared equals to mgy. Therefore, v is equal to 2gy. So then if we plug that in back up there, we have finally that the time is y1, y2, there should be a dx out here. Two g dx. All right. So this is our model equation, and we want t to be a minimum. So we want to minimize t. So we're going to solve this equation for minimum t, right? How do you do that? That's how you minimize a function. But what we have here is an integral, or a functional, a function of a function. And so yeah, you're right. And if it was a function, you'd take the derivative and you set it equal to 0 and you solve that, and the root of that equation would be the minimum. But it doesn't work for a functional. We have an integral here. So we want to minimize an integral. How do you do that? So it turns out, I mean, you probably don't know. Who said variational theory? Okay. You've had a course in calculus variations? Okay. So, I mean, other than someone who's had a course in calculus of variations or seen it in some other course, you probably don't know how to do it. But this is exactly the whole realm of the calculus of variations, is how to minimize basically functionals or integrals, okay? And so with that, I'm going to switch back over, and I'll make these notes available to you guys. And the rest of this lecture, I'm not going to do any more. It'll just be the notes here. And so, yeah, basically, just to kind of reiterate the problem, we're interested in exploring sort of all the paths, all of the possible paths between those 2 points. Okay? And this is where the calculus of variations comes from. And the basic idea of the stationary value of a function. So, and I give some notes there. I'm gonna kind of speed up because I want to get through this by the end of class. But if you want to read what I have to say here, I'll make these notes available and you can say it. So basically, the stationary value of a function is where the rate of change of any possible in any possible variation is 0. Okay, that'd be a stationary value. And the easiest way, or the easiest example I like to think of here, is like a marble in a bowl, right? It's obvious where the stationary value of that marble is, right? It's at the bottom of the bowl, because at the very bottom of the bowl, if I move it in any direction, then the rate of change is basically 0. If I make any kind of infinitesimally small motion. And so if we consider a function that's in this case, a function of x and some functions of x. So this is actually a functional, right? Because u is a function of x, okay? And we investigate a virtual change or a small change in u, okay? And here I'm defining them with finite values. Here's my mouse. So basically I'm saying that the del u, or a small variation in u, is equal to some very small scalar that tends towards 0 and some arbitrary direction, phi, some arbitrary direction cosine, right? Well then if I want to look at the change in the function, then it's simply the function evaluated, plugging in, with all these arbitrary chains in the u's minus the original function. That's the change in the function, okay? And so if we take that change in a function and we Taylor expand in powers of epsilon, okay, then eventually we arrive at this last equation. And of course, epsilon is something that tends towards 0, right? So we can say that the first variation of f is the limit of this, the change in f over e or over epsilon as epsilon goes to 0. And therefore, from what we just derived, you can see that you have this guy, okay, this last equation, okay. But I think in the next slide So finally we have that the first variation of f is equal to this, and if you compare that with the total differential of f, you have with the total differential of f, you have this first term that's a function of x itself, and so these variations are performed in an instant in time, or just with holding time fixed, okay, and performing these little variations. And so that's what makes them different than a kind of standard. So then, there's just more. I'm trying to go fast here. I want to get finished, but there's more kind of information about what I mean here. And we say that these direction cosines are arbitrary. So in order for f to be stationary, right, then the right-hand side must vanish. And if these direction cosines are arbitrary, meaning they could be anything, right, because of the way we defined them at the very beginning, then for that to be true, for this to have a stationary value, then this statement must hold, okay? So these are just some general notes on the calculus of variations. And this del operator, it is, it's an operator like the differential operator, but not exactly the same as I showed, but it's similar. And because of that, it also has some similar properties in that it's, it's commutative, and you have a chain rule and a quotient rule and product rule and all these things, okay? It's also commutable with the differential operator. So if you have ddx of a del function, well, and then I prove this by just substituting finite quantities back in for a second, but you can show that it's commutative with the del. So you can switch the order of operations with the differential operator. And we can also show the same for integration. And so then there's also this thing called the fundamental lemma of the calculus of variations. And it basically just says that if you have an integrable function g of x, then this statement is true if n of x is arbitrary, okay? So if n of x is arbitrary, then g of x must be 0, okay? And we can show that by if eta, that's not n, eta, if eta is arbitrary, then it can be anything, then we could let it be equal to g of x, and then if you plug that in, you see that g of x has to be 0, okay? So I encourage you to kind of go, we'll sort of use these tools in the background, but I want to show the mathematics that motivate all of the stuff. The finite elements actually has a very, very strong mathematical backing, and that's why it's so well accepted. And it's all rooted in the calculus of variations. But so I encourage you to go look at these notes in more detail and go a little slower through them. But basically now we have that the stationary value of a definite integral, which is what we need to do to solve our equation for the Brooke-Christochron problem, right? So if we use the del operator to investigate the stationary value of a definite integral, I'm basically just doing some mathematics that are consistent with the way I've defined the variational operator there. You basically see eventually that after some manipulation, some integration by parts and other things, that what we arrive at, basically you have this equation here, and you say because of the fundamental lemma of the calculus of variations, that this del y is arbitrary, then what's left for this to be stationary is that what's left is the integrand here has to be equal to 0, and this thing is called the Euler-Lagrange equation, okay? And so what we can do with this is we can just apply this. So the integral I of a function f will have a stationary value when this statement is true. And so we can use that to solve our problem, right? So we basically just plug in the integrand, f equals the integrand of what we derived earlier, and you apply the machinery of the Euler-Lagrange equation, and then solve it, and you have your solution. Because your solution to this problem is a path, right? It's a function. Okay? So let's do it. Well, so now I'm mixing in code here, so I actually use some SymPy in Python here. But basically, I define our function. The function is the square root of 1 plus y prime squared over 2gh times y. That's exactly what I wrote down, right? So that's our function. I symbolically perform this Euler-Lagrange equation machinery on it. So basically, take the differential of the function with respect to y, the differential function with respect to y, and then again with respect to x. Simplify it all, set it equal to 0, and you get this equation. But if you notice, I couldn't make it simplify further, but if you notice, all we really care about is this term, right? Because it's equal to 0, I can multiply the denominator out, and I can divide by this first term. So really what we have here is just this second term in the numerator, and you can see it's a differential equation. I know it's hard for you guys to see, but that's d squared dx. So this thing right here is a differential equation that we need to solve. And the solution to that thing is there. It's a cycloid. So this path is the path that will get you there in the minimum time. And so it turns out you can, here I just solved it numerically. I just solved that differential equation numerically and I plot the solution. But you can actually come up with an analytic solution, and it turns out it's these equations, and those are the equations of a cycloid. And so then just for fun, let's make our own numerical experiment. So here's our race, right? Remember the YouTube video, right? So here's our race. I'm going to put 3 particles right there. This is the path of a cycloid. This is a straight line. And this is just some other arbitrary thing I made up because I didn't know exactly, in that YouTube video what the top path is. Okay, so I think I just, some quadratic function or something I made up. I'm going to put 3 particles there. I'm going to let them accelerate under time in a numerical simulation, and we'll see which ball wins the race. So anybody want to change their vote now? Which path is going to get you there the fastest? Red, blue, or black? Yeah, we know that now, right? We know. So we know. With that, let's run our race. Let's run our experiment. Okay. So this is just some background on the calculus of variations, and this is sort of the mathematical fundamental stuff that we'll be using when we use finite elements. So these are the deep-rooted mathematics behind the whole theory. This is, you'll see some of this stuff, but just wanted to motivate it all here today. All right?